Guys, welcome to part 2 of our HESI math review. For those of you guys who didn't get a chance to watch part 1, you might want to go back and check that out first. Part 1, we talked about, I know that's probably hard to read, but we discussed fractions, which is a big one on the HESI. Fractions, and big for anybody who despises math. Everybody usually hates fractions. So in that video, we discussed how to add, subtract, multiply, and divide fractions. So definitely really important for the HESI. We then also went into ratios and proportions. I definitely would watch that video if you haven't had a chance to. I would go back and watch part 1 first, because proportions are actually going to play a key role in the first part of today's video. Proportions, we discussed how you can cross multiply to solve for a missing number. So go back and check that out, as that's going to be really important. And that in that video, we also touched on measurements. So with those measurements, you know, when we're converting cups to ounces and pints to milliliters or what have you, proportions also could play a role in that. So I reviewed that in that video. So go back and check that out. Today, we're going to start with percents. We're going to get into how you solve percent questions, like what is 50% of 80, or 35 is what percent of 95, you know, whatever. We'll look at those types of questions. And then what we do, there's some other ways that we can apply those percent questions and how you might see them on the HESI. When I say conversions, you know, I know a lot of times people think conversions. Well, we did conversions when we were converting measurements in the proportions video, but in this case, we're looking at different forms of numbers. We're gonna, you know, haven't already been exposed to fractions, ratios, and percentages. I want to take those different forms of numbers and convert them amongst each other. So we're going to take a look at that today, and how we can convert a decimal to a fraction and vice versa, and how we can convert that decimal to a percent and vice versa. So we'll take a look at that. Basic algebra, we'll get into a few things like how we solve for x, maybe even take a look at some integers, and then we'll later get into military time, as that's also a big one on the HESI, and something that's really important in nursing as well. It's really important to know how to use military time as opposed to our standard time, because that's what you guys will use in the field. So we'll take a look at that as well. So let's get started. We get rolling with our percents today. So percents, just as a kind of a starting point here, the word percent, just to break that down as kind of a key understanding for percent, literally means per. When I say cent, think of like a cent, like a penny, meaning 1/100th of a dollar, right? So percent literally translates to mean per 100. So that's a big thing today as we look at our percentages. That's gonna come in handy to know that means per 100, or sometimes meaning out of 100, right? If I got a 75% on a test, it means that I got 75 out of 100. So our magic number in this section here, what we're looking at with percents, is 100. So here's what I mean by that. With percent questions, you might get a lot of questions, maybe on the HESI, that says something like, what is 15% of 85? Or 26 is what percent of 30? Or, you know, even you might get 32 is 45% of what number? So each of these questions, we're asking something different. So some of us, when we were taught percents, you may have been taught, well, when I'm trying to calculate the percent of something, all I have to do is take, like in this question, some of you guys may have been taught to take 85 and multiply it by 0.15, which is the decimal version of a percent. And that is correct. You would absolutely get that question right. But we actually approached this question and this question totally differently. You may have been taught to take 26 divided by 30 to figure out what the percentage is. So see, we're doing different things. In this section, I want to show you how we can apply, knowing how to solve a proportion from part 1. I want to show you how we can apply that knowledge, and each one of these questions will be answered the exact same way. So here's what I mean by that. Going back to what we know about proportions. Proportions, we take an unknown and set it equal to a known, right? We looked at that in our last video. For this, there's kind of a formula you can follow. Anytime you're asked a percent question like this, when you're trying to solve for a percent or where a percent is involved in the question, what you can use is you can use the formula that says percent over 100 is equal to is over of. So it's a formula that we can follow, and is over of is going to also translate to be part over total. So you can use that as well. If you want to, if you're more familiar with that, and I'll show you why that would work. Is over of typically is just something I use because that's the language used in these types of questions. As you can see, we have what is or of 30 here. So you can see that language using that is and of. And it keeps us kind of where it's the same every time. You know, if you remember in the last video, we talked about how one side is your known and the other side is your unknown. And that's still going to be the case here. But no matter what, we're always going to have a percent go over top of 100. Whatever your percent is goes over top of 100. Your is will always go on top of your of. So no, it depends on the question being asked on which side is the known and which side is the unknown. So let me show you what I mean. Let's answer each one of these questions, and I'll show you how it's set up a little bit differently, but following the exact same formula. All you have to do is plug in those values according to that formula. So let's start with this one. This one says, what is 15% of 85? So you can see what we're going to do is we're going to follow that formula. We're just going to plug in our values. So based on what the question says, you can see here it says, what is, so technically the is the question mark here. That's what we're asking for. Our percent, we know that we have a percent. So we know that's going to be the number that goes over top of 100. And you can see here, it just literally says of 85. So how we're going to plug that in, remember our percent goes over 100. So 15 goes over 100. And then our is, which is our question mark here, that's our x. So remember the is always goes on top. So that's why x is on top here. And it's asking out of 85. Again, also known as the total of 85. What we're asking here, what is 15% out of a total of 85? You know, so that's another way to look at that. I'll show you how we can apply these types of questions a little bit further. But that's how we set that up. So you can see the first side is our known because that's the side that has the two numbers in it. And the other side is our unknown. Either way, we solve proportions by, again, remember from the last video, we cross multiply and then divide. So let me get my calculator clear to show what that looks like. So we cross multiply 15, we always cross multiply the side opposite of the x, remember, so 15 times 85 is 1,275, and then divided by 100 is 12.75. So here our is 12.75 is our answer. And the next question, we're going to plug that in. Let me erase that to get that out of the way. The next question, we're going to, again, apply the same formula, but here the x is going to be somewhere different because of what we're asking for in this question. In this case, it tells me 26 is. So it gives us the is in this question. It says what percent, so here, that's our question. So there's going to be our x of 30. So you see how we plug this in to solve this percent question. Remember, your percent always goes over top of 100. So in this case, since that's what we're asking for, there's our x. On the other side, 26 is, so 26 is what goes on top, out of 30. So when I cross multiply, I'm going to go opposite from x. 26 times 100 is 2,600. And then dividing that by 30 gives me 86.6 repeating. So we can call that 86.7. Okay, so that one we can just round it to 86.7. Maybe I should get into rounding a little bit later in the video as well, because we'll talk about decimals. So rounding is going to be pretty important, depending on, in math, sometimes you're asked to round a certain way. So in this case, we were rounding to what's called the tenths place. I'll get into that. So that's how we got that answer. In the last question, let's do the same thing. You know, again, we're going to follow the exact same formula, but we're asking for a different number. So again, in this case, the x is going to be a different location. So here we can break this down. Also gives us 32 is. So that it gives us our is, gives us our percent as well, just like in the first one, but this time it's asking for the of. So our X is gonna go on the bottom this time. So there again, our percent always goes over top of 100. So 45 goes over top of 100 in this one. Our is always goes on top of. So the question says 32 is of what number? There's our X. So again, as usual, we're just gonna cross multiply. So I'm gonna take 32 times 100 to get 3,200. Dividing that by 45 gives me 71.1 repeating. So we'll just round that to the 10th place as well and call that 71.1. So you see what we've done in every single question based on what was asked. You can see in the first one, we were looking for the is. So that top number right above our of was our X. In this question, we were looking for the percent. So that's why the number over 100 was our X. And over here, we were looking for the of. So that's why the number on the bottom was our X. But you can see, no matter what, we're always following this same formula. So it doesn't matter what's being asked. We just simply have to read the question, see what's being asked of us, and then plug that into this formula here, where again, remembering that that 100 is always going to be there, because remember, we're solving a percent question, and percents translate to mean per 100. So it's always out of 100. So remember that anytime you have a question that asks for where a percent is involved, you're asking for an unknown number and a percent is involved, then that formula will be useful, this proportion formula. How we can apply that, every now and then you might get questions. The biggest place you might see percent questions is when you're asked to calculate percent discount, like at a store, if something is 45% off. We can calculate that. We can use that same formula the same way we did just a second ago. So if let's say we have a question that says the cost of a jacket is $85, but today it is 25% off. That's an exclamation point there. What is the cost of the jacket now? So there's a couple different ways that you could apply this, but I always kind of start with, first we got to figure out what the discounted, what the price is that we get to remove. So we don't take $25 off of 85, right? Because it's not $25 that's the sale price, it's 25%. So our first thing that we have to do, even though this question isn't listed, we have to ask ourselves this question: what is 25% of that full price, 85? So again, that question isn't listed, but this is a way that we kind of ask ourselves to figure out what that discounted price is. How much do we actually get to take off of this jacket? Well, let's follow our formula here and asking ourselves this question: what is 25% of 85? Well, 25 is my percent, so it goes on top of 100. I'm trying to solve, it's asking me for the is, so that goes on top of a total of 85. So what this means is when we calculate, when I take 25 times 85, I get 2,125. Dividing that by 100 gives me 21.25. In other words, $21.25. Not the end here, right? All I did by asking myself this question is I was calculating what is, if it's 25% off, well, what is 25% of that full price? So this means I get to take off, just like it says here, it's 25% off, which translates to mean $21.25 off, because it's 25% off that price. So now, since it's asking us for that final cost, I'm going to take one last step and take $85 minus that discount. And I'm going to get, what's 85 minus 21.25? $63.75. So there's my final price. There's my end answer. That's what I get to pay for this item. Now, some people will take this question and may say, well, if I get to remove 25% of the cost, that means I'm left paying for 75% of the cost, right? 100% of the cost, or the full price, is $85, right? That's 100%. I get to remove 25%, leaving me to pay 75% of that jacket. So some people may instead ask themselves, what's 75% then? And if you did that, if you chose to do it that way, which is totally fine in these types of questions, a lot of times I just like to see what I get to take off because it makes me feel better. I'm getting this savings, right? But some people like to go directly to that full price. And if you did that and asked yourself, what is 75% of 85, that's totally fine. What you're gonna end up with is $63.75, because you're just going straight to that final cost, because that's what you're left to pay with. So totally up to you on how you solve those types of questions. That's just a different way of thinking about it. I always like to find, like I said, I like to find the discount first because I like to know what I'm saving. So up to you guys on that one. But that's how we can apply these types of percent questions with percent discounts. Let's say we can even use it percent increases too. In all of these application questions, typically you're trying to solve for the is, if that helps. But let's say right now, price of gas is, let's say, $3.60. I don't know what it actually is right now. It might be close to that. $3.60. It is expected to increase by, let's say, 6% next month. What will that make the final cost of gas? Okay, so let's see. Same exact situation here. It doesn't mean that it's going up $6 or 6 cents. It means it's going up 6%. So we have to ask ourselves first, let's ask ourselves that magic question then. What is 6% of the current cost, $3.60? So by asking ourselves this question, we can see what it's expected to increase by. So money-wise, what we're doing is we're translating, we're simply just converting the percentage to what that means in terms of dollars and cents, right? Because that's what we're dealing with here. We're dealing with money. So I want to see, well, then what is it going to increase by? So let's find out. Well, 6%. So again, 6%. So that goes over top of 100 out of the current total cost, $3.60. So that means when I cross multiply here, always away from the X, it's going to be 6 times 3.6 to give us, let me make sure I did that right, 6 times 3.6 to get, I got two different things each time, fat fingers, 2160, but then dividing that by 100, 2160 divided by 100, not times 100, gives me 0.216. So in other words, and then I'll round this because I'm dealing with money. So money is typically rounded to the 100th place, which is the second place after the decimal. So this would round to 22 cents. So that means it is expected to increase, since we're talking about an increase here, a little bit different than our percent discount that we were talking about in the previous question. This is an increase or a gain. So that means it's expected to increase by 22 cents. So that means we would add that. $3.60 plus 22 cents, right? That's what 6% is of that cost. That means by the end of the month, we're expected to see $3.82 for the cost of gas. So that's just a different way of applying these percent questions. So just a way to think when you get these word problems, again, think about what we have and what the question is asking us and how we can apply that with what we know. We know how to solve these percent questions with our percent formula here. So keep that in mind. Okay. So that's the biggest thing you'll probably see with percents and how we can answer those percent questions and how we can apply different word problems with percentages. So now I want to take a look at conversion. So I want to show you guys, now having seen fractions and ratios and percentages and a little bit with decimals, we may touch on rounding of decimals a little bit later. But with decimals, you know, we've kind of had some exposure to those decimals, especially here in these types of questions with money, how we can convert those to each other. So one that's pretty easy that I think everybody kind of is familiar with is the fraction 1/2, right? 1/2. If I were to convert that into a decimal, that would be 0.5. Some people are familiar with that. And I'm going to explain in this section how we get from there to there. So I'm gonna break this down a little bit further. If you weren't aware that that's the same thing, but this is the same thing, fraction, but this is the same number, but just in decimal form. Last video, we talked about ratios and how fractions and ratios are very much almost the same thing. So if we were to ask to convert that to a ratio, 1/2 is the same thing as 1:2, the ratio 1:2. And then later, we're also going to see that decimals and percents can be converted pretty quickly amongst each other. The decimal 0.5 is the same thing as 50%, which makes sense too, right? If I got half of the questions right on a test, I got a 50% as my grade, right? So that's another way to think about that, that half it equals 50%. Half of $1 is 50 cents. Another way to look at that. So this is what we're looking at here, are different forms of numbers that can be converted amongst each other and some popular things that you'll see with those. So this is our fraction form, decimal form, ratio form, and percent form. So let's look at how we apply these. So the first thing I want to show you is how we convert a fraction to a decimal. So I'm going to leave this fraction up here on the board, and you guys, we just saw this, I just erased it off the board. We know that 1/2 is 0.5, but how do I get there? Anytime you have a fraction and you want to convert that to a decimal, we're simply going to look as if that line right there between the top number and the bottom number, or between our numerator and our denominator, is a division line, as if that says divide. And all you have to do, it's easier to just do it in your calculator, although you can do it by hand. You could take 1 divided by 2, but in your calculator is just going to spit the answer out for you. So you'll have that available to you. So 1 divided by 2 is going to give us 0.5. If just on a whim you decided I don't have a calculator, I want to see how to do that by hand, you could do that. 1 divided by 2 looks like this. 2 does not go into 1, so just jogging our memory on that long division we probably did a long time ago. Since 2 does not go into 1, what we can do is add a decimal and a 0. So this is still 1. It's just, we can look at it for the purpose of this division question, we can look at it as 10, right? But instead, we're going to put our answer over here. That decimal will go just above it in our answer. 2 goes into 10 5 times. You can see where that 0.5 is coming from, because 5 times 2 is 10. So when I subtract, I get a remainder of 0, which means I'm at a stopping point. So 1 divided by 2, as you guys can see, gives me 0.5. Like I said, highly recommend using that calculator, as that's going to be much faster. So every single time, no matter what your fraction is, if you have 3/4, 3 divided by 4 will give you 0.75 in your calculator. Every single time, top divided by bottom. Look at that line in between as if it says divide here. 3 divided by 4. And last video, we saw that not all fractions look like this. Every now and then you might have what's called a mixed fraction or a mixed number, which means that there's a number in front of your fraction. If you have, say, 8 3/4, super easy here. All that means is there's not a 0 in front of the decimal. It's now an 8. Whatever your number is in front of your fraction simply just matches the number in front of your decimal. So anytime you have a number and a fraction, so let's say 2 5/8, we know that this is going to be 2 point something. All I have to do is take 5 divided by 8. I think 5 divided by 8 is 0.25. I want to make sure, 0.625, yes. So 5 divided by 8 is 0.625, or it says in your calculator, it gives me 0.625, but remember that 0 is being replaced by the number that's already there. That 0 is just because all I did was 5 divided by 8 in my calculator, so that was 5/8. So 5/8 by itself, yes, is 0.625. But because that 2 is already there, that 2 replaces that 0. So this is 2.625. So make that a little bit easier. That anytime you have a number in front of your fraction, that'll be the number in front of your decimal. And in a second, when we look at decimal to fraction, you'll see that that applies the same way, going the other way. So all you have to do to remember fraction to decimal is top divided by bottom. Okay? Whereas then now going the other way. Let's say I have a decimal and I want to convert that to a fraction. So let's use our initial example up here because we know what the answer is going to be, but how did I get there? So we know from our first example that we had on the board, we know that this is half. Again, how do we go from 0.5 to half? Well, anytime you have a decimal, what you want to do is you want to get rid of the decimal. You want to look at this number as a whole number first. So when I say whole number is the decimals at the very end. We don't have to write the decimal if in a whole number because it's at the very far right. So what that means is I'm going to move this decimal as many times as it takes to get it to the very end to take this from 0.5 to now 5. So that's going to come into play. What happens is the 5 becomes the top number or the numerator of my fraction, and the denominator is based on that movement. So that movement, we don't just move a decimal and don't do anything to it. That we had to do something in order for that to happen. So decimal movement, think about place values in our decimals. Place values, everything is based on tens. So tenths, hundredths, thousandths, and so on. So when you move a decimal one time, your denominator, you're moving by a tenth. So you're going to see as we get some more examples going here, moving a decimal 2 times would be you move by 100th. So that's 100 will be your denominator. If you move it 3 times, your denominator will be 1,000. So one thing to remember, if it helps when you're converting decimals to fractions, remember as many times as you move your decimal, that's going to mean how many zeros are in the denominator. That's a way that just an easier way to remember that. So you're thinking, wait a minute, I thought you said the fraction was 1/2. Let's go back to remember part 1, we talked about with fractions, you always want to reduce your fraction. So remember with reducing fractions, as long as the top number and the bottom number can both be divided by the same thing evenly, do so. So 2 wouldn't work here, right? I can't divide 5 by 2 because it would give me 2.5. That's a decimal. I don't want a decimal in a fraction. I want to make sure I can divide them both and get a whole number as both answers. That's what I mean by dividing evenly. Again, go back to part 1 if we need some practice with that. So here, since they're both multiples of 5, I'm going to divide them both by 5. 5 divided by 5 and 10 divided by 5. Here at the top, 5 divided by 5 is 1. 10 divided by 5 is 2. So there is your fraction answer. And sometimes, guys, when you end up with large fractions, you want to double check to make sure you did that reducing properly. Now that we know how to convert a fraction into a decimal, you could always double check your answer by taking top divided by bottom, and you should get that original decimal. If you do, that means you're correct. So obviously we saw that one already, but let's look at another one. Let's say I have 0.45 as my decimal. So again, remember I deal with the decimal to turn it into a fraction. I'm going to move it as many times as I can just to get it to the very end. And that turns that number into the number 45. That's our whole number. That becomes the top number of our fraction. But remember, the number of movements is going to determine what our denominator is. So again, 1 movement is 10, 2 movements would be 100. I know the temptation is to say, oh, I moved it twice, so it must be 2. No, remember decimal movement is always by tens. So 10, 100, 1,000. So here, moving it twice means 100. 2 movements equals 2 zeros. And then from there, I want to go ahead and reduce this. 45 over 100. Again, remember anything that ends in a 5 or a 0 is a multiple of 5. So let's start there. These are pretty big numbers. Let's see if we need to divide that even further. But starting with this small number is helpful to see right away. So 45 divided by 5 is 9. 100 divided by 5 is 20. And looking at our fraction here, 9, I know I can divide that by 9 and get 1, but 20, I can't divide that by 9. 9 divided by 3 would work. 20 divided by 3 would give me a decimal. This means I cannot divide both 9 and 20 by the same thing, so this is my reduced fraction. Seems like a large fraction, seems crazy that that's my smallest form, but it is. Sometimes that works out that way. And the same thing we talked about in our previous conversion, anytime you had a number in front of your fraction, that was just the same thing in front of your decimal. Well, the same thing applies here. That instead of just 0.45, what if this was 6.45? What you can do is look at it as if it's 0.45, focus on just what's after the decimal point, because I know whatever's in front of the decimal point is simply going to remain the number in front of my fraction. So a second ago, we just did that. We looked at 0.45, converted it to 45 hundredths, said that that's the same thing as 9/20. So again, if this was 6.45, this would simply be 6 and 9/20. Whatever that number is in front of my fraction, in front of my decimal, is the number in front of my fraction. It just stays the same. And that's how you convert a decimal to a fraction. Okay. Last week, we also looked at ratios, and I explained that ratios and fractions are pretty much the same thing. So we saw a second ago that the fraction 1/2 is simply just 1 to 2. The difference between fractions and ratios, I had mentioned in the last video that fractions are typically used to show a part to total relationship, while a ratio is typically used to show a comparison relationship. I'm showing 1 is to 2, you know, that's that comparison. Where this is 1 out of 2. But for the purpose of just converting it from one form to another, that's all we're doing. Instead of one number on top of another number, instead it's 2 numbers written side by side separated by a colon. That's the difference between fractions and ratios here. So if I had the fraction 5/8, that would be 5 to 8. Fairly simple. The difference would be, again, as we saw a second ago, that not all fractions are simply just a number on top of another. Sometimes we might have a whole number in front of it. And remember, that's a mixed number or a mixed fraction. So instead of just 1/2, if this was, say, 3 1/2. In the last video, when we talked about fractions, we talked about how we can take mixed numbers and turn those into improper form. If we do that here, what that's going to give us is it's going to give us a number on top of another, in turn giving us our ratio. So if I was asked to turn this fraction into a ratio, what I can do, if you remember, turning this into a mixed number, or turning this mixed number into an improper fraction means I'm going to take 3 times 2, which is 6, plus 1 to give me 7, and the denominator stays the same. So 3 1/2, guys, is the exact same thing as 7/2. Okay, it's just a different form of that fraction. But now that I have just 2 numbers, that's my ratio. Ratio will always be just one number compared to another number. So fractions and ratios will always be the same, but you might have to first turn that fraction into a different form. So if you see a fraction like that, that's how you would convert that to a ratio. Make it improper first. Okay. And then looking at decimals and percents, in our example, we had the decimal 0.5, and we said that that was the same thing as 50%. So anytime you're converting a decimal to a percent, keep in mind, remember that percents translate to mean per 100. So 100 is going to be our magic number here. When you're taking a decimal and you want to convert that to a percent, what you're doing is you're actually multiplying it by 100. But a quicker way to do that without having to use your calculator, anytime you multiply any number by 100, what happens is the decimal point moves 2 places to the right. Remember, we just talked about that decimal places are based on tenths. So 10, 100. So if you multiply 0.5 by 100, what ends up happening is your decimal point goes 1, 2. So that 0 in front of the 5 can be dropped. This empty space right here is going to be a 0. So that's where that 50% comes from. And you notice I didn't write the decimal in here because when the decimal ends up on the very far right, it's understood to be there. It's just, it makes this the whole number 50. So decimal to percent, you can either go ahead and use your calculator and say, well, that's times 100, or if it's easier, just remember 2 places to the right. So I'll just use RT, 2 places to the right. So if I had a decimal, say, let's just say 0.63, that's 63%, because again, I'm taking it 2 places to the right. If I had the decimal 1.8, that's going to be 180%, because I'm taking that decimal 2 places to the right. If I had the decimal, let's say 0.625, that's going to be 62.5%, because I'm moving it only 2 places to the right, so that makes my decimal there land between the 2 and the 5. Always just 2 places, because in turn, again, remember, we're multiplying it by 100, so that's why we're only moving 2 places. And then you guys probably know what we're doing when I'm going from a percent to a decimal. Opposite, I'm going percent. If I have a percent and I want to convert that to a decimal, what's technically happening is I'm dividing it by 100 instead of multiplying. And you guys know what's going to happen with our decimal. What that means is our decimal is moving 2 places to the left. So that's what happened with 50. Remember, 50 doesn't have a decimal point in it, but all whole numbers, it's understood to have that decimal at the end. So I'm moving it 2 places to the left, and that's why it ended up there in front of the 5. And you'll notice, guys, too, this is something that's kind of relevant here. I took that decimal point and moved it 2 places, so that ended up 0.5. Really important with decimals, the 0, anytime you have a 0 at the end, so yes, that 0 was originally there, right, with the 50. But now that it's behind a decimal point, trailing zeros behind a decimal point are irrelevant, so they can be dropped. Anytime you have a number that starts with a decimal point, you want to put a 0 in front of it, because that helps us to see that decimal point a little bit clearer. And that's going to come in handy when you get into your nursing classes too, because especially in healthcare, anytime you have a small amount of medication that starts with a decimal, it's really important that you have that 0 there. And that's going to be the proper way to write that, because if that decimal gets lost, it could look really, really confusing. Let me give you an example. If I needed to administer 0.5 milliliters of medication. So say the prescriber wrote out this prescription and said that we need to give a patient 0.5 milliliters. Well, that looks good. Let's say that decimal is hard to see. Well, now it says 0.5. Something is triggering in as the nurse, I go to administer this medication, I see 0.5 milliliters. Well, I'm going to go talk to that prescriber, and I'm going to say, okay, did you mean 0.5 or 5 here? Because that 0 is throwing me off. But if that prescriber wrote 0.5 milliliters and that decimal gets lost, if I can't see it because they wrote it really quickly, that's the problem with decimals sometimes, is they're small. If that decimal gets lost, what am I administering this patient? 5 milliliters. The difference between 0.5 milliliter and 5 milliliters, depending on the medication, could be a really big deal. So making sure that anytime we have a number that starts with a decimal point, that 0 is going to be really important. So just kind of a little side note there. Okay, but keep in mind, we're going back to our percent to decimal. So percent to decimal, always 2 places to the left, no matter what that percent looks like. Let's say you have just 4%. The whole number again, so that decimal starts behind the 4, going 1 place, puts it in front of the 4, 2 places, puts it in front of a 0. So this would be 0.04. You'll notice that that 0 is important because here's where the decimal ended up. So that 0 right here after the decimal point is important because it holds the place value between the decimal and a non-zero number. If there was a 0 back here, that's different. That's a trailing 0. So that's why that gets dropped. And once again, since this number again is going to start with a decimal, I put that 0 in front of it. So anytime, and again, if it's helpful, guys, using your calculator is going to put the zeros in the right place for you. If you took 4, well, my example was 4%, it was written up here. If I took 4 and divided that by 100, your calculator will give you 0.04. Okay, so it's gonna put those zeros in the right place for you, so that might be helpful. So that's how we convert amongst our different forms of numbers. So you guys may be thinking, well, hey, you didn't show me how to convert a decimal, a fraction to a percent, for instance. No, but knowing what I know, okay, so let's say I take the fraction 3/4 and I want to know what that is as a percent. So there's not a direct conversion for fraction to percent, but I do know, right? I know how to convert a fraction to a decimal, right? If I take 3 divided by 4, that gives me 0.75, right? Well, now can I turn that into a percentage? Absolutely, because I know how to convert a decimal to a percent, right? Decimal to percent, we just saw that a second ago, was either times 100 or moving our decimal point 2 places to the right. So this is 75%. So the fraction 3/4, your answer here would be 75%. So sometimes you just have to take what we know. There might be an intermediate step before we can get to our end answer. Okay, so again, if this said turn this fraction into a decimal, fraction to decimal, top divided by bottom. But fraction to percent, we still had to do that first to make sure we could then get to the percent. And that might be the case in some questions. If I have 6% and I want to know what that is as a ratio, let's say. Well, there's two ways we could look at this. One, I do know how to convert that into a decimal, but with percents, sometimes percents, you can always remember percents mean per 100, right? So 6% is also the same thing as 6 out of 100. But remember with fractions, we need to reduce that first, right? 6 and 100 are both divisible by 2, right? They're both even numbers. So let's start there. 6 divided by 2 is 3. 100 divided by 2 is 50. 3/50ths, I can't reduce any further. That's a fraction, but as a ratio, remember we just write that side by side. So there was an intermediate step there. I just turned it from a percent to a fraction first. Or again, some of you guys may have looked at that and said, well, 6% to a decimal is moving it 2 places to the, 2 places to the left is 0.06. But 0.06, we know decimal to fraction, right, converts to this because we move our decimal all the way to the end to make this 6 out of 100, which then reduces. So really kind of multiple ways to get to the same answer. That's the beauty of math, right? So up to you on how you guys did that one, but our end goal there was to get to that ratio. So those are our conversions. So that's how we convert those different forms of numbers. Okay, so our next step here was to get into, what was our next? Basic algebra. So a couple things with, when I say basic algebra, couple things that I think may show up on, I'm looking at some of our feedback from HESI exams, and most of those that say basic, like just say algebra or basic algebra, I'm interpreting that to represent solving for X. So solving for X in those types of problems. I do want to introduce integers to you guys first, which is positive and negative numbers. And the only reason why I want to introduce that is just in case you see that in some of those types of questions where we're trying to solve for X. If you have some type of problem and you need to solve for that unknown number, if you see a positive or a negative number, negative sometimes throw us off. So I want to show you how we can apply those. So looking at positive and negative numbers, the whole time we've been working with numbers, we've been working with positive numbers. But negative numbers are just a little bit different because we're not used to using those. And the way that we look at those and how I oftentimes compare positive and negatives, think about positive numbers is something that we have. Let's think about money, right? That's money that I have, right? If I have the whole number 6, this is the same thing as positive 6. Positive numbers, you don't have to put that plus sign in front of it. This still represents positive 6. So positive 6 is like saying I have $6, right? Whereas negative 6, I owe $6. So oftentimes that's where we're going to see positive and negatives more often is in terms of money that I have and money that I owe. So that's the difference between positive and negatives. But in this section, I want to show you guys how we can add, subtract, multiply, and divide with positives and negatives. So adding integers, and that's what they're called, numbers that have, either positive or negative, they're referred to as the term integers. So when I say the term integer, that's what I'm meaning. Adding integers that have the same sign. So meaning they're either both positive or they're both negative. That's really easy. All you're going to do is add them together and keep the sign. So let's use 6 again, and let's add it to, say, 4. So just dealing with kind of small numbers right now. We know 6 plus 4 is 10, right? What we did was we took positive 6 and positive 4, and that became positive 10. So that's what I mean, where we have the same sign, we just simply add them together just like we always do and keep that sign. But another way to think about that is if I have $6 in one pocket, I have $4 in another pocket, I have a total of 10, right? You guys are thinking, okay, this is like second grade math. Where are we going here? Okay, I promise I'm going somewhere. We're going to apply it the same way. If I have -6 plus -4, and you might see parentheses around this question because a lot of times math textbooks or the HESI exam might want to separate the operation symbol from the integer symbol. So that's the only reason why you might see parentheses there. But this still means -6 plus -4. The answer here is going to be -10. Because again, negative plus a negative equals a negative. When they're the same sign, we just simply add them together, keep the sign. Or in other words, if I'm at the store and I owe $6 for one thing, I owe $4 for another thing, I get to that cashier and I owe a total of 10, right? So there's my money example here. This is pretty simple. When we're adding integers that have the same sign, we simply add them together and keep that sign. Cool. What happens when they're opposite signs? Well, let's take a look. This is going to be applied a little bit differently. If I have, let's say, 6, and I'm adding that to -4, it's going to be a little bit different here. So let's think in terms of my money again. Let's say this means that I have $6, but I'm trying to buy something that's 4, so I owe $4. I'm going to leave that store with $2 in my pocket, right? Because I came in with 6, I paid 4, I left with 2. Here's what's happening. When you're adding integers that have the opposite sign, so one's a positive, one's a negative, what ends up happening is you're simply taking the difference, or you're subtracting their two values, so 6 minus 4 to get 2. And you're going to keep the sign of the larger value, so the 6. Let me give you another one and show you what I mean by that. Let's say this was reversed. Let's say this was -6 plus +4. So again, opposite signs. So again, when they're opposite signs and you're trying to add them together, I'm taking the difference of the two values. So I'm still getting 2 in this case because it's still 6 and 4. But instead, since 6 is a negative, so is my answer. Whichever one is your larger value is going to be the answer or the sign in your answer. But again, if it's easier, think of this in terms of money. I owe $6 for something, but I only have 4. I still owe 2. Is another way to think about that. So opposite signs, we're taking the difference. If you need to, think about that, this way, again, you're taking the difference between their values, but you're keeping the sign of the larger value. And it doesn't matter which one's in front. In some cases, that larger value may be second. So if I have, say, let's say 3 plus -7. I don't know why I'm focusing on numbers that come up to, anyway. So in this case, I want to say 10, but that's if this was 3 plus 7. That's the temptation. Not the case here, because it's 3 plus -7. So opposite signs. 3 is positive, 7 is negative. So remember, that means I'm taking the difference between their values. The difference between 7 and 3 is 4, right? So that's what I mean by that. It doesn't matter which one's first, which one's second. I'm taking the difference in their values, and then I'm going to keep the sign of the larger value. So 7 was negative, so is my answer. If I have, let's say, -2 plus 14. Again, the difference in their values, 14 minus 2 is 12. And because my 14 was positive, so is my 12. Because I'm looking at the larger of the two values. But again, if it helps, I owe $2 for something and I have 14, I'll leave that store with 12. I still have $12. So those are opposite signs. So far I've looked at addition. Addition of the same sign, we simply just keep them together and add, or we go ahead and add them together and keep that sign, right? If this was positive 2 plus positive 14, my answer is 16. So it's a little bit different when we have those different signs in there. So same sign, simply add them together, keep the same sign. Opposite signs, that's where we take the difference between those two values and then keep the sign of the larger value. All right. Subtraction. Subtraction's fun. Subtraction's a little bit different. Subtraction, now again, if I had, say, 6 minus 4, we know that that's 2. Okay, right? We can easily do that. We've got, you know, here, the signs aren't going to be relevant, or they will be, but let me explain. In subtraction, especially if we're thinking in terms of money, let me use that example. Let me give another example. In this case, I have $6 and I took away 4, so that's why I was left with $2, right? Let's say I owe $6 and I take away 4. Totally different now. Here's what's happening. Here, my answer is going to end up being -10 here. Because here's what this is. With this, as far as in terms of money. Here, this shows that I owe $6 to the bank, right? That I owe $6. But I go pull up to that ATM and I subtract another 4, money that I think that I have. I now am in debt $10 to the bank, right? So again, that's a way to think about this in terms of money. But here, subtraction can get complicated. So what I say is we remember our rules for addition, right? Addition said same sign, add them together, keep the sign. Opposite sign, take the difference, sign of the larger value. So subtraction, let's do this instead. Let's instead, if you remember from the first video, remember in fractions when we were doing division and we said keep, change, flip, and we just applied our multiplication rule for division. We can do the same thing here, kind of a keep, change, but instead of flip, we're making the opposite. So the thing that I always remembered with subtraction is anytime you come across subtraction, you can always remember the phrase add the opposite, which means instead, what I'm going to do here, so let's pretend like I don't know the answer is -10. What you could do is you can turn this subtraction into addition and turn the second number into its opposite. So here, since this is +4, I'm going to turn it into -4. And now you can see where that -10 comes from. Let's just apply our addition rules that says negative plus a negative. I'm simply going to add those two together and keep the sign. So you can either remember the phrase, anytime you see subtraction, you can remember the phrase add the opposite, which means you're going to turn it into addition, change the second number into its opposite. If in the previous video when we talked about fractions and you remember keep, change, flip, maybe you'd like to kind of apply that here and remember this as keep, change, opposite. That's what we're doing here. We're keeping the first number always. The number in front never changes. We're changing subtraction into addition. And then the second number becomes its opposite. And that's what I mean by opposite, that if it's a negative, it just becomes its positive. If it's a positive, it just becomes its negative. And then we just think back to our addition rules. So let's say I have, I don't know, how about -14 minus -2. So here you guys are looking at this, you want to say 14 minus 2 is 12, but we're going to apply this a little bit differently here. Instead, and actually that's going to end up being somewhat correct, but let me show you why. Because again, we see subtraction, so let's change it into addition. Well, that's a plus. And then the second number becomes its opposite, so -2 becomes +2. So now I have -14 plus +2. My addition rules say that when I have opposite signs, I take the difference between the signs but I keep the sign of the larger value. So since 14 was negative, so is 12. So that became negative 12 as my answer there. Okay, so subtraction, I know that can be complicated, but again, just remember the phrase, add the opposite whenever you see subtraction, or keep change opposite. Multiplication and division is much easier because all you have to remember, same sign means positive. Opposite signs means negative every single time. So I'm using 6 and 4 as kind of our magic numbers here, but we know 6 times 4 is 24, right? That's because it's positive 6 and positive 4. Same sign means positive answer. So that's actually going to be the case when I have negative 6 times negative 4. I'm still going to get positive 24 here. No matter what, my answer is still the same. No matter what, I'm still going to get, as I always would. 6 times 4 is always going to be 24. But the difference is whether or not it's positive 24 or negative 24. And that here, again, the temptation is because we know our rule for addition says a negative plus a negative is a negative. But in multiplication, it's like they kind of cancel each other out. Okay. The only time you end up with a negative is if you have mismatched signs. If I had a negative 6 times 4, so that's a negative times a positive, now I get negative 24. And I would get the same answer if it was 6 times negative 4. Opposite signs simply means negative answer. And the same thing applies for division too. Anytime you have division, remember, same sign means positive, opposite signs means negative. So if I have, let's say 35 divided by 7, we know that's 5. That's just one way to write division, but again, we know that that could be 35 divided by 7. If it's negative, then that means if one of them is negative and the other one's positive, I still get 5 as my answer, but in this case, it's negative 5. So in multiplication division, that's all you have to remember. If the signs are the same, your answer is positive. If the signs are opposite, your answer is negative. So again, I show you those integers just in case I don't know if that is something that comes across in the HESI. I haven't taken the HESI, but I'm going based on feedback that comes back from HESI exams, and it just says algebra. And to me, integers are very much involved in algebra. So that's something that I like to show in case you ever do come across positive and negative numbers and we're not sure what to do with those. Okay. All right. So that comes up because I want to show you guys how we solve for a missing component in algebraic questions and algebraic equations. So if I ever have something like this that says, that says 10 plus x is equal to 12. This is a pretty easy one. Anytime you have a missing number in a question like this is easy because I know 10 plus 2 is what gives me 12. And you're trying to solve what this is. Okay, right now we're going to pretend like we don't know what it is because, again, sometimes it won't always be this easy. But how we solve for that unknown number, if you ever have a problem like this, you have an equation where I've got, this is called an expression over here, this 10 plus x. If that equals 12 wasn't here, this would simply be what's called an expression because there's no equal sign. It doesn't tell me what it's equal to. And I wouldn't be able to solve this because I don't know. It says 10 plus x. It doesn't have that's equal to something. Expressions are sometimes helpful. You may come across an expression maybe when you're using substitution, which means like you may get a question that says, if x is equal to 5, what is 10 plus x? If that's the case, then you can just substitute in 5, and we know that, well, then 10 plus x is going to give me the answer is 15, right? So you may see substitution where we have to do something like that, but that's if you ever have just an expression. In an equation, because I know what this whole thing is equal to, I should be able to solve for that missing number. I should be able to figure out what that is based on the fact that I know what the answer is to this problem right here. And how we do that, an easy way to do that is simply just by doing the opposite of what's currently being done. So what I mean by that, since we are adding 10 to x, if we were to subtract 10, do that over here. If we were to subtract 10, what that does is it cancels that out and it leaves me with x by itself. But what happens is, because this equal sign means that this side is literally equal to this side, then whatever I do on this side of my equation, so I'm gonna put an imaginary dotted line here. That's what I mean by sides. That this side of my equation, I've got to do the exact same thing on this side to keep it equal. That's what that sign means. So I'm going to subtract that 10. 12 minus 10 gives me 2. So there's my answer. It says that x is equal to 2. So anytime you have an unknown number, whether, and I say that x is the most commonly used variable used in these types of questions, but if you ever see A or B or C, it doesn't matter. Any letter oftentimes is used just simply meaning an unknown number, and you just have to solve for that number. And that works by just doing the opposite of what's being done. So let's say I have x, well, let's, in fact, I just said that. Let's use k minus 3 is equal to 15. Again, this might be pretty easy. It's something minus 3 gives me 15. Well, again, to get k by itself, that's the idea here, to get k by itself, to say k is equal to something. That's my end goal. Right? That means I need to get rid of this 3. Since 3 is currently being subtracted from k, I'm going to add 3 because that's going to cancel that out on this side and leave me with k by itself. But I have to do whatever I do on one side of the equation, I have to do on the other. 15 plus 3 is 18. And I had mentioned substitution. Substitution works here if you're ever trying to check to make sure your answer is correct. You know, my answer says, excuse me, k is equal to 18. If I substitute that in for k in the original problem, because the original problem said that k minus 3 is equal to 15. Well, if I substitute 18 in for that, is 18 minus 3 15? Yeah, absolutely. So that means I did that correctly. So that's a great way to double check your work. I'm going to get to some bigger questions. These are just kind of showing you, you know, when we're adding, when we're subtracting, if we're multiplying, if you ever have, say, let's say 5a is equal to 20. Whenever you have a variable right next to a number, that simply means multiplication, that those two numbers are being multiplied. So this says 5 is being multiplied by a. So again, to solve for a, to solve for that unknown number, I have to just simply do the opposite of what's being done. Since a is being multiplied by 5, I'm going to divide by 5, and that's going to cancel that out, leaving me with a by itself over there on the left side of that equation. But I have to do the same thing to both sides, and 20 divided by 5 is 4. That gives me my answer. And then same thing if our variable is being divided. If I have, say, I don't know, let's say m divided by 4 is equal to 6. I'm trying to solve for m. I want to get m by itself. So m is currently being divided by 4. Let's multiply by 4 to cancel that out. But just make sure you do the same thing on the other side. 6 times 4 is 24. So that means m is equal to 24. So all this is relevant because sometimes you might have bigger questions or bigger equations where multiple things are being done. You might come across something like this. Let's say it says, we have a question that says 5x plus 7 is equal to, let's say 13. I think this is not going to come out super evenly, but let's see. No, it will not. It will end up being a decimal. That's okay. Sometimes our x is going to be a decimal, so sometimes it's not easily done in our head. So let's take a look at how we apply this here. So anytime you have two things being done to your variable, in this case, I'm multiplying by 5. I am also adding 7. In this case, you want to actually do the opposite of what's being done. So we're going to think, going back to, if you recall, your order of operations. Does anybody remember that? Your order of operations? Either we remembered PEMDAS or please excuse my dear Aunt Sally. which said that anytime I have a problem, I have a big problem. This is different from this. This is totally different. This is solving for X. So this is what I mean by opposite of order of operations. Our operation said that if we have a very large problem, maybe we'll do a couple of those too at the end here. If I have a very large problem that has some multiplication, some exponents, some division, whatever, I've got some addition, this is the order we need to follow. That parentheses needs to come first, exponents need to come second, multiplication and division comes third, addition and subtraction comes last. And that's if I'm just trying to solve a problem. Here, it's already solved, I'm just trying to find X. So when we're trying to solve for X, like I said, we're thinking in the opposite because I'm trying to solve for that unknown number. So opposite of our order of operations means I'm going to get rid of whatever's being added or subtracted first. That's typically the last step in our order of operations. And then I'm going to get rid of whatever's being multiplied or divided next, because that would be the step right before it. So that's what I mean here when I say opposite of our order of operations. We're going to get rid of that 7 first. If I got rid of the 5 first, we might not get the same or the correct answer. So again, to get rid of a number, when I'm trying to solve for this X here, to get rid of it, we're doing the opposite of what's being done, but making sure we're doing it to both sides, right? So here, this ends up giving me 5x is equal to, because the 7's canceled out, haven't done anything with the 5 yet, 13 minus 7 gives me 6. So then now I still have to solve for X. X is not by itself. So to keep going, I'm trying to get X by itself. Right now it's being multiplied by 5. So I need to divide by 5 to get rid of that. To get X is equal to, dividing that by 5 is going to give me 1 1/5. So 1.2, right? I'm brain dead these days. Yeah, 1.2. So 6 divided by 5 gives me 1.2 as my answer. So always remember that if multiple things are being done to our X, we're still getting rid of these numbers, but thinking in terms of opposite of our order of operations. So let me do another one. Let's say I have, let's do this. Let's say X divided by -3. That's when these negatives might come in. And I am then taking that and subtracting 5 is equal to, well, it doesn't matter. It can be a decimal. Equal to 21. All right, well, it'll end up being a whole number because we're multiplying at the end. Anyway, okay. So remember, opposite of what's being done. So here's our equal sign. So here's our imaginary line. We're thinking of left side of the problem versus right side of the problem. Whatever we do on the left, we also have to do on the right. Remember, we're going to get rid of this 5 first. Okay, get rid of whatever's being added or subtracted, and then whatever's being multiplied or divided here, in this case, divided. So -5 means I'm going to add 5. I'm going to do that to both sides. So that's going to leave me with X divided by -3. The 5s had canceled out, so that's what's left on the left over there. On the right side, 21 plus 5 is 26. So I'm left with X divided by -3. Don't be thrown off by that negative. We're still approaching it the exact same way. I want to get X by itself. Since it's being divided by -3, I'm simply going to multiply by -3. Multiply by -3. Cancels out over there, leaves me with X by itself, which is what I want. Over here, 26 times -3. Remember our rule for integers says I'm going to multiply those numbers just like I always would. 26 times 3 is 78. However, since it's a positive times a negative, remember, mismatched or opposite signs means my answer is negative. So my answer here would be -78. And again, you can always double check your answer. Sometimes when you have a lot of steps, you might want to double check that. If I'm saying that -78 is my answer, could I plug that in for X and get that in the answer? Well, -78 divided by -3 is simply 78 divided by 3, which is 26. Because again, negative divided by negative, same sign means positive answer, right? So 78 divided, or negative 78 divided by negative 3 is positive 26. Positive 26 minus 5, is that 21? Yes. So we did that correctly. Okay. And that's how we solve for X in these questions, in those algebraic equations. So I mentioned the order of operations only because, again, in a problem, when I mean order of operations, is if you have a big problem that says something like this. Say you have multiple things and you're just trying to solve the problem, the equation. Say you have, that doesn't have an unknown variable in it. You're not trying to solve for an unknown, but if I have, say, 3, I don't know, let's say times 2 plus 4 squared plus 6 plus 1. Well, anyway, yeah, let's just stop there. Let's look at this for right now. What I mean by order of operations, remember I wrote down, please excuse my dear Aunt Sally, a way to remember that, or some people remembered PEMDAS, but it's PEMDAS to remember our order of operations. But just simply remember M and D go together and A and S go together. So it's really a 4-step thing that we're looking at here, meaning that this simply means how I solve this problem is I need to follow this order in order to get it correct. So parentheses comes first, which means any type of operation within parentheses. If this said 4 and then parentheses around 6, this just means 4 times 6. There's not an operation inside the parentheses. That's just simply a number inside the parentheses. So this is a multiplication problem. But in this question we have up here, I do have an operation inside the parentheses, so I want to solve that first. And my recommendation for order of operations would be to make sure that you always rewrite your problem, taking it step by step. So I'm going to solve parentheses first, and then I'm going to answer. So this is, I know 6 plus 1 is 7. So that means I'm left with 3 times 2 plus 4 squared plus 7. See what I mean? That we want to make sure that I'm using that order of operations and rewriting it along the way. E stands for exponents. So a little side note for exponents. Anytime you have a tiny little number on top of another number, that's an exponent. Exponents simply just mean to take that number and multiply it that many times. So not to be confused with 4 times 2, this means 4 multiplied twice. So it's not 8, it's 16. Okay, so again, that's what that means. 4 squared means 4 2 times. Okay, if it was 4 cubed or 4 to the power of 3, then it would be 4 multiplied 3 times. If it was 4 to the power of 4, you get where I'm going here. Anytime you see an exponent, it means to simply take that number and multiply it that many times. So here in this question, I have 4 squared, or 4 to the power of 2 is another way to read that. So to solve that, again, like I said, that's 4 multiplied twice. 4 times 4 we know is 16. So that means I'm left with 3 times 2 plus 16 plus 7. So I'm left with multiplication and addition now. So step 3 is looking for any multiplication and division. And in that case, guys, I'm reading it from left to right. A lot of times people read that order of operations and say that multiplication has to come before division because that's the way it's written. That's not the case. They go hand in hand. They kind of coincide with each other, which means division, in reading it from left to right, if division happens to come first, then we're going to solve that division first. We read it from left to right. In this case, in this particular problem, we only have multiplication, but that's what I mean by that this goes hand in hand. So reading it from left to right, we will solve whichever one comes first. In this case, 3 times 2 is 6. So that means I'm left with 6 plus 16 plus 7. So last step is addition and subtraction. Same rule applies there. Reading it from left to right, if subtraction comes first, we'll subtract first. If addition comes first, we add first. And here we're left with all addition. So I'm just going to quickly add that together. 13 plus 16 is 29. All right, 6 plus 16 plus 7. Okay. So that's our order of operations. So that's the biggest thing I think that people miss in the order of operations. I see those things that go around social media all the time and everybody's arguing on what the correct answer is. That's the biggest misstep, is they forget that multiplication and division go hand in hand. Here's what I mean by that. If I had something that said 4 divided by 2 times 3. Or let's do an easy one that we can do in our head. Times 2. A lot of times people want to go ahead and say, well, multiplication is supposed to come first. So I'm going to take 2 times 2, which is 4. And then 4 divided by 4 is 1. 1 is a wrong answer here. Because, like I said, multiplication and division go hand in hand. So at this point, we read it from left to right. And whichever one comes first is what we're going to solve first. So actually, 4 divided by 2 is 2. So that means I'm left with 2 times 2, because I solved that first. And now I'm left with 2 times 2, which is 4. So the correct answer here is 4. And the same thing applies for the addition and subtraction. If addition comes first, yes, we'll add first. But if subtraction comes first, subtract first. So if this was, say, 4 minus 2 plus 2, again, same idea. A lot of times people say, well, I have to add first. So I'm going to take 2 plus 2, which is 4, and 4 minus 4 is 0. So the answer is 0. Wrong. Instead, we read it from left to right. 4 minus 2 is 2. So there's my answer there, plus 2, my answer is 4. So keep that in mind. And that applies for anytime you have a large problem that has any addition, subtraction, or multiplication, division, we always read it from left to right. So just a little, like I said, a little side note, make sure we keep in mind the order of operations always when applying that algebra. Okay. Last thing I mentioned I want to talk to you guys about, and this is super easy, I think, once you kind of get the hang of it. Military time can be brand new for some people, and we've just never seen it before, and it's a total foreign language. That makes sense. We're not used to seeing it. But in military time, the difference is very simple. In standard time, we are used to, like thinking of a clock. I wish I had a wall clock in here. I don't even have a wall clock to use as an example. We usually have wall clocks in all of our classrooms, but not today. It's a 12-hour clock, right? And we typically, in a 24-hour day, that clock goes around twice in a day because we have AM and then PM. We start at 12 midnight, and then we end at 11:59 PM before it becomes the next day. But what happens is we have two o'clocks, right? We have 2 5 o'clocks. We have a 5 o'clock AM and a 5 o'clock PM. The difference is in military time, or sometimes referred to as international time, there's no difference. There's an 8 o'clock, there's an 8, or which is called 0800, so that's 8 AM. And then there's 2000, yeah. So that's the difference, is that we're seeing there's 5 AM, which is 0500, or there's 1700, because that's the difference. That's 5 PM. So here's how this works. Military time is always going to be written using 4 digits. Okay, so it's always 4 digits no matter what. I know when we have like 5 AM, it's just 500, so there's 3 digits. Different here, that would be 0500. So I'm going to show you all this. So it's always using 4 digits. We never use a colon to separate the AM, to separate the hours and the minutes. And then you don't have to write AM or PM. Okay, and our minutes are always going to match. Whatever our minutes are on standard time, that's always going to be the same. So really, it's just kind of getting to know these hours, the difference between all the hours. So here's what I mean. Let's think about this. And like I said, the difference is, well, let me write standard time first. The difference is, we have a clock that's a 12-hour clock that goes around twice in a day, whereas a military clock starts at 0, makes its way to 24. Okay, that's another way to think about that we just go from 0 to 24. So 12 AM on a military clock is 0 100 hours. The first two zeros represent that 12-hour time, and then the minutes are gonna always remain the same. So this is the 12 o'clock AM hour is always gonna be represented by 00. Some of you guys may be watching this, maybe have some military experience and say, well, midnight's always 2400. That's okay. That is okay. It's kind of looked at as the end of the clock sometimes, that's the end of the previous day. But then 2400 is the last, that's it. You can't go beyond that. 12:01 AM. So for instance, when our clock starts counting, 12:01 AM has to be 00. It's not 24:01. And 01 represents the minutes. So that's why I always teach that 12 AM is 00 hours. It's the very start of the day. We're not even 1 minute into the day, so it's 00. And then 12:01 AM is 0001. 12:15 would be 00:15. You see what I mean? That the minutes stay the same. It's just that 12 o'clock hour will always be represented by 00. Okay, because we're only 15 minutes into the day, so that's why it's 00:15 for 12:15 AM, because we're just showing that we've only been 15 minutes into this day. Okay, so 1 AM, we're now into the first hour of the day, so that's where that 01 comes in. And then again, the minutes stay the same, so this is sometimes referred to as 0100. 2 AM is going to be 0200. 3 AM is 0300. We're simply, those AM times are going to look very, very similar. 4:15 AM is 04, and then the minutes stay the same. So 04:15. It's 4:15 AM. We'll see where we're happening here. We're going 6 AM is 600. 8 AM is 0800. 10 AM is our very first double-digit hour. Okay, that just simply means we're not putting that O in front of it. So this is going to be 1000. Still very, very similar. We're now 10 hours into the day. 11 AM is an 1100. 11:30 AM, you see very similar times here. It's just going to be 11:30. Okay, then I get into 12 PM. Our clock is now starting over. Okay, we've gone from 12 AM to now 12 PM. But a military clock simply just keeps counting, right? Instead of 11 AM was 1100, 12 PM is now 1200. We're just halfway through our 24-hour day. So then 1 PM, let's see where we're going here. We're just continuing to count on, is now 1300. These afternoon times are really the times that it takes to remember that these are the times we're not used to seeing, right? Our morning times looked quite similar, so that made sense. But these afternoon times, I'm not used to 13, 14, but that's why. It's simply just continuing to count on until it gets to the end of our 24-hour day. So you guys get the idea. 2 PM is going to be 1400. 3 PM is going to be 1500, and so on and so forth. And again, your minutes always stay the same. So a trick to remember those afternoon times, if it's helpful, anytime after 1 PM, you can always just add 12 to the hour. And that helps to remember that hour. So adding 12, that makes that 13. 3:20 PM would be plus 12, that would be 15, and then the minutes stay the same. So 3:20 PM is 15:20 on a military clock. So that helps us with the afternoon times. That would work every single time. If we just want to remember how we change the hours. Again, the minutes just always stay the same. They're always going to match. Or I have some people that like to use a clock. Okay, how we're used to seeing a clock, right? We count all the way through 1, 2, 3, 4, 5, 6 o'clock, 7, 8, 9 o'clock, 10, 11, 12. Now let's go to the outside and draw 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. What I've drawn up here, inside the clock represents our AM times with the exception of these 12s right here. As again, just remember 12 AM is the beginning of the day, so that's your 00 times. And then 12 PM is the middle of the day, so that's going to start with 12. But if you remember, inside the clock represents AM, outside the clock represents PM. So if I said to tell me what 5:30 AM looks like in terms of military time. Well, remember inside the clock, it simply kind of looks the same. That's gonna be 0530. Remember, always 4 digits, so that's why we wrote the O in front of it or the 0 in front. No colon and no need to write AM or PM. Because again, there's a difference. If I told you to tell me what 5:30 PM now looks like, well, that's different. 5 on the outside of the clock is 17, minutes stay the same. So the difference was 0530 for the AM time and 1730 for the PM time. So the clock is pretty helpful. If you have that on a note sheet, you can always draw that clock. Just draw 1 through 12 on the inside, 13 through 23 on the outside. And remember that the outside is your PM times. So if I said 8:17 AM, remember that's just 0817. That looks the same. But 8:17 PM, right? Outside the clock is 20, so that's gonna be 2017. And that works every single time. So that's the difference between your military time and your standard time. And you'll see some military time questions on the HESI as well. All right, well, I hope that helps. That's a quick review of just a handful of things that are on the HESI. Please don't hesitate if you guys run into any questions. You guys can always reach out to me. You can just talk to your admissions rep and say, hey, I've got some math questions for Ellie. I'd be glad to help.